Hello there. So in the previous video, we took a look at how the make and the make files work and how the make utility helps us automate execution of commands. And what we are going to do for today's video is run some experiments that will enable us to understand this last file here, last from the test directory, which is the linker script. So we want to make a case as to why a linker script would be required. And again, just to give you a hint as to what the linker script does, it helps us control the placement of code. Placement of the code and data, right? The question is, why would we want to do this and what is the need for the linker script? Okay, so towards this end goal of understanding the need for linker script, we are going to run some exploration and experiments. So let me propose a modification to our makefile, which is this option here, the minus w comma minus Tmain.ld. This was the option for the linker. And again, we have our assembly code here, which we said goes to the assembler. And then the assembler sends it to linker. The linker does some magic and then it becomes machine code, right? So what we are, and well, in our case, we were using the GCC compiler. So the GCC compiler essentially calls the assembler and passes this. So this was a way to tell GCC that, hey, please pass this minus Tmain.ld to the linker. That's what this did. And what we are now wanting to do is eliminate that linker script and see what happens. So let's go ahead then and delete this much part. Okay, right. And well, I think a good thing to do here would be first to retain that part, run the experiment, then undo it so that you can see the difference a lot more clearer. Or a lot more clearly. So I'll need two terminals. I'm going to drag this here. So we have one terminal. I'll press the plus icon here and go ahead and create another one. Both of them should be pointing to tests. So we are in test now. And then in one of them, I'm going to run the make debug command. Okay, and it complains that we do not have the main.elf, which makes sense because we should have done make first. And now we have the main.elf here, because of which if we did make debug, the QEMU would be launched. And remember, the QEMU would start off and wait for GDB to connect. That's essentially what this S option does in QEMU. So okay, we'll go on the other terminal and write make GDB, and then it connects with the QEMU. And notice that it is pointing very nicely to our assembly code. And notice this value here, which is x870. Right? So that's the value where it's pointing at. Now, we'll not go any further in this experiment here. We'll just exit. The key point here is, remember, the value of PC and the fact that we were seeing this code here. That's important. Okay, so let me exit out of GDB. Yes, let me use Control A followed by X to terminate QEMU. Now let's go back to the make file, and okay, let me also get move this aside. Now let's get rid of this. Okay, let's go back here. Now remember, we have modified the make file, but we haven't generated another ELF again. So to do so, what I'll do is do a make clean. So previous ELF is deleted. If you can see here, it doesn't exist anymore. And then I'll do make. Now, an important thing to note is this right here. It says that, hey, I did not find the underscore start symbol, which is strange because we have it here, right? And we did supply it with this file, but then why is it not finding? So that has to do with the fact that we need to export that symbol or expose it, and the way to expose it to the linker, essentially make it available globally. So what we are going to do is we are going to use a assembly directive called globl, globl, not global, it's globl. And recall that anything that starts, I don't know if I've mentioned this earlier, but anything that starts with a dot and then has like some name next to it is called a directive, an assembly or assembler directive. And what that does essentially is guides the assembler on what to do. So this one is guiding assembler saying, hey, I want to declare a symbol that's global, that should be exposed to or rather that can be found anywhere. If there were multiple assembly files, it could have been found in the other one. Or if it is used in the other file, know that it is okay. So that's the idea of exposing things globally. So what we are wanting to expose is start. Okay. So I've saved the file. So, and then what I'll do is I'll again do make clean. And then after that, let me do make. Now, if you see, so the assembler is kind of happy. It's complaining a little bit about end of line character. So that's easy to get rid of. We'll just create like a new line here. You'll notice the new line here, and we'll just save it. And then let's go back and again do make clean, do make. This is interesting. End of file, not at end of line, new line inserted. Okay, whatever. I do not know what this means, but okay, this warning we can ignore for now. But note that it goes ahead and completes. Now the question is, will this run? The instructions are same as before, everything is same. Then let's do make debug. Again, QEMU is launched. It's waiting. Oh, okay, I see. Let's hang on a minute here. So the problem was that I did not save the file. So let me go ahead and save the file, which yes, I have done now. And okay, let me go ahead and what is happening? Interesting. So if I draw this and then, okay, finally done. Okay, so the idea is let me save the file, then I'll go here, do a make clean, and then do a make. And now you see that there are no warnings here. All good. Okay, that's what I wanted to demo very quickly. So it had to do with the fact that I did not save the file. Now let's go ahead and do make debug. And here let's just clear the screen and do make GDB. What happened? Where is GDB? Now, if I press Control C here, we see that, there are some issues here. First off, program counter is pointing to 0. It's not pointing to x8 7 zeros. That's where we should have had it. It's not there. So what's going on? And, yeah, essentially, it's the CPU, the assembly is not displayed because it cannot access the 0th address. So something is fishy here. And to explore what fishy stuff is going on here, we have to explore the idea of memory map. We have to understand that for the virt machine, which is right here, that we are using on QEMU, who is where and where is what, memory is where is the CPU trying to fetch the instructions from, and so on and so forth. And now to kind of find answers to this, we will need to go to this file here. So which is available, okay, let me just mention, which is available at this URL, and this is the source code for the QEMU, and within that the RISC-V virt machine. This is the implementation for that, and you can see it here also here as well within RISC. 5, we are within the virt.c file. And this is because, the memory map for QEMU is not documented, so I had to jump into the source code and figure it out. And this is also, by the way, how I understood why our code should start from the hex 870's address, and that's what I'm trying to demo here. So note that, well, the 0th address is here, and the idea of memory map, first off, is that you have addresses starting from 0 to some n, which are divided into various sections or various so-called peripherals, right? And recall from the first lecture or video, we said that there is a CPU, there is memory, CPU floats the address, memory returns back data, and so on and so forth. So now we were just looking at memory, but the thing is, this is like a huge address range, and some part of it is actually memory, and other parts can be some peripherals, some time or something. And we'll come to those much later when we are dealing with when we are dealing with, let's say, embedded systems and trying to program, let's say, the UART and other things. We'll come to that later. But the important thing for this video is memory components, and you see a memory here and then another memory here, right? So this is called the read-only memory, called the ROM, and this is the dynamic memory, dynamic random access memory, which is the DRAM. And my claim is that our main.elf, the contents of it, which are the instructions, assembly instructions converted to machine code, those are supposed to sit here. That's my claim. And I know it, again, based on experience and based on the way QEMU works. And I'll demonstrate also that to you. But then we also see a memory here at hex 1000. So what happens is each machine, each embedded system will typically have some ROM. Manufacturers typically have like put their specific code there. And so the CPU will execute the ROM code initially, which I'll demonstrate now. And after it has executed that minimal code of initializing other things, it will jump to the code memory where the user's executable code is available. And by user, I mean the embedded programmers or another company's code is available. So for example, if, let's say NXP makes a microcontroller, MCU, then it'll have its own ROM little bit that does some NXP stuff. And then there will be another memory available where, let's say, I, as a programmer from X company, XYZ company, will keep the code. And then this together will be our solution. This is what we'll sell in the market. Hopefully I did not confuse you so far. So the idea then is there is a ROM, and ROM has some vendor specific code, and then from the vendor specific code initializes something and jumps to the user executable code. So in this case then, my claim is it will first start off here, execute bunch of instructions, and then jump here, right? That's the idea, and let me just demonstrate that to you. To be able to demonstrate that, what I'm going to do is I'm going to delete few more keywords from the Makefile, and those are the GDB-EX options, or values of those options. So what are these doing? So we ask the GDB to connect to the QEMU, and then after that we ask it to execute two commands saying, hey, put a breakpoint on the start symbol, which happens to be, by the way, at the address this in general meaning when we had the linker script. Now we don't have it here, so the statement is false. And then we would ask it to continue, right? And we would actually ask it to continue. So what continue means is, hey, start the execution and go a little further. And that's how it would come and pause here, right? And now my claim is that once we remove this, right, and save this, then go back and bring this back here, exit QEMU, then go here, right? And now if I were to do make clean, make, and then make debug, make GDB, you'll notice that the program counter is at the value of x1000, which is the value exactly for the ROM here, right? So my next claim then is that if I were to do ni, keep an eye on the program counter value. If I were to do an ni, at some point it will just change to the value of, so it's executing, yeah. Now if you see, it was executing some initialization code, a few instructions. Now if you see, it's hex, okay, let me just write it, hex 8 7 zeros, right? And if now I were to do an ni, we see that, it is lost. And if we now do Control C, we see the situation that where we left off. To search and discuss about the memory map, we are back at the same level here. Right. Then the question is, the reason this went, or rather the answer is, the reason this went rogue or went in a bad state like this is because at this address, there was nothing available. Our code wasn't there. So this then brings us to the fact that somehow we need to arrange our code here, put our code here. But then the mystery that is unanswered is, why is this even working without a linker script? Why is this working? There is no linker script specified anywhere, but it still runs, or, the commands go through. Okay, so we are going to peel that onion now, and we are going to try and answer what is going on there. Remember, the question is, we did not supply a linker script and it is still working. So let me exit out of all of GDB and QEMU. Now what I propose we do is we do RISC-V unknown ELF LD and do like a minus verbose. And we see something here, output. And my claim is that this is a linker script. And the interesting bit here is, which should be explained here, it's like using an internal linker script. So my claim is, when we did not provide linker script, the linker used an internal version. And as per the internal version, it went ahead and place the content in the memory. Again, the details of the linker script is something that we'll come to in the next video. For this, I just wanted to make that case as to why it's important and run some experimentations. But now you can see that, this was an internal linker script that it ended up using. And if we do not provide one, linker always uses the internal linker script. Okay, that was one thing. And then the question was, it generated an ELF, and how does that ELF look like? Where is the starting point for that ELF? And the answer to that is, we are going to again invoke another utility called readelf, pass the -a and -w option to it, and then ask it to read the main.elf. What this is going to do is print the diagnostic information or more information about the ELF file. And the interesting bit here, a slight detour essentially. So the main.elf file has like a lot of sections inside of it, and somewhere in between there is code, right? The bin file, on the other hand, the main.bin file, it only has the code, right? So that file, bin file, is available here. The ELF file is available here. We can load either one of them in QEMU. We typically prefer loading ELF so that QEMU can make use of this extra information and help us print or help us debug the binary better. That's why we are using ELF. But then what information is available here? We see that there is a header, the ELF header, and this header kind of has different information. The one that is of use to us, or that should concern us, is this entry point address, which is hex 10,054. So it chose that as the starting address and put all of our code there. And we can actually go ahead and, try and see this within QEMU as well. So let's go there, and I'm going to have to search some commands for GDB in a while. So let's do this, make debug, make GDB, right? So remember, the address we are interested in is hex 1054. That's where the juicy content is. And let me go ahead and find GDB command to see to view instructions in memory. And let's see what comes up. So there are certain commands, disassemble or something like that. Address string. Well, actually, how about this? Let's just go ahead and print, use this, let's see, bytes. Okay, n format and u. So I'm going to use I don't know, word hex 4 maybe, and 0x10054. Oops. Okay. How should the address be? It just should be in hex, is it? Okay, repeat count, format, and unit size. So unit size, okay, unit size is word, format should be x, and repeat is I'll go with 10. So 10, format, size, done. Syntax error, expression here. Okay, let's just go with this then. Nice. So do you see how do I print mode? Let's see. Unit size, byte hex word, so it was word, format, and okay, let me see. Is it word? How do I go about printing many of these? Well, either ways, I suppose the important point is that we see our start symbol placed here. And if we would go ahead and print, let's just maybe manually do it. Let's just print the 8th. Okay. Never mind. So I should have seen this earlier also, but I'm blind. So it cannot access that memory also. GDB is unable to reach that memory. But kind of from the ELF, it is figuring out that that's where the start symbol is, which is fine. That is what I wanted to confirm anyways. Okay, so now the question is, we wanted to move the start to the hex 80,000. Not 80,000, sorry, hex 8 followed by 7 zeros. That was our plan or our idea. So let's get out of this. Let's get out of this. Oops. Okay. Let's get out of this, right? Let's go back to make. And now, just to close the video on the right note, we'll go to the linker script. And again, remember the syntax and all of this. We'll start looking at that starting next video. And once we're done with the linker script, we will explore load and store, and then from there we'll go to C. So with more 2 videos, we should be done with the basics to have a solid foundation of C. Okay, so now let me then go ahead, undo all of the things here. And well, what I have undone is added this here, and this is added. This will delete again, just so that we can see the jump from the ROM code once again. Okay. Right. So I'm going to save this file. Again, we are providing our own linker script now. Go back to the shell. Go back to the shell here. Then do like a make clean. Then do make. Now we are going to do a read ELF again to confirm few things. And okay, a lot of stuff is printed. And what we are wanting to look at is the entry point. Now the entry point is changed. It's hex 8 followed by 7 zeros. So that's important. So it looks like our binary is updated. And now what we'll do is we will do make debug and make GDB. And if you see, again, program counter is at this value, which is hex 1000. And now we are going to keep on doing ni until it reaches this line here. Right? So this is the initialization code. And we'll do ni, right? Ni, again. Now the interesting bit is you should see that it is going to execute this last instruction, which is jump register T0. T0 happens to be this, which has the value of the hex 870s, right? Again, remember that this was the ROM code, which is manufacturer or vendor loaded. In this case, this was like 5 lines of assembly, and it is jumping to this memory address now, and that we shall quickly see. Now if I do ni, boom, program counter is pointing to hex 870s. We have all our good code here. And now if we go ahead, and continue to execute this, we'll see that all of these are incrementing and decrementing, and it is performing essentially loop, which we saw like 2 or 3 videos back. So with this, hopefully I should have convinced you about a couple of things. First, we made some modifications to the Makefile to eliminate the usage of the linker script, and then we generated an ELF out of it, which was loading the program at hex 10,000 or 1054 address. And then after that, what we did was we analyzed how without the linker script it produced the ELF, and that had to do with an internal linker script that the linker uses. We explored the idea of memory map and reasoned about the ROM code and the DRAM memory location. And now hopefully I've convinced you that a linker script is required to put our code in at the start of the DRAM region. And I'll just quickly highlight that once again, which is okay, just a moment. Our DRAM is here and our code had to be here. So hopefully that is something you're convinced with. In the next video, we'll look at how to write a linker script, and then after that, load and store operations, and then we'll start off with our journey of C. So thank you for hanging around. This was quite a long and maybe even, an information overload kind of a video. Thanks for hanging around, and I'll see you in the next one. Bye-bye.